First, I would say that our future progress with simulations of galaxy evolution, from the computation point of view, they depend on three simple things. We want more computing power to allow better resolution. We need higher accuracy of the codes, and most importantly, certainly, we need more complete and realistic physics models. And ideally, all three of these things need to be advanced. Normally, and that's what I a bit critique now, I think it's starting to get dangerous. Normally, we all should concentrate primarily on this third point. And that's definitely most interesting. And that's what we need to do. But I would argue if we ignore the other two things, we are going not to be competitive in a few years anymore with those people who also address these two other points. And I think it's very dangerous to just do this, because that will mean that you'll soon be outdated and will not be able to use the power that is upcoming from the big computers. The number of cores is growing exponentially. This is the new thing since a few years' time, because that is really what has changed. In the past, we could just keep the old codes and they would run faster with every new generation of computers. And that is not the case anymore to a large extent, because the individual cores do not get faster much anymore. It's even possible they might get slower, because maybe we go to more energy efficient cores in the future that are slower individually. So that is really bad, because it means that to get an increase in computational power, you need to use more and more cores, and they are now exponentially growing. So it's not the speed of the individual cores that's exponentially growing, it's the number of them. And that's a total change of the game. If you look at the so-called top 500 list of supercomputers that is published once or twice a year, I think, this big supercomputing conference. This is from last November. I think you can probably hardly read it. But number one now present is Titan in the US. This is a AMD-based Cray machine, accelerated with K20 GPUs from NVIDIA, the newest generation. Now, if you look at this, these numbers you probably can't read here. The number of cores this machine has is 560,000. Sequoia, Blue Gene Q on number two, has 1.5 million cores. Now, all of these supercomputing centers, they would like you ideally that you use all of them. In fact, in the US, in the DOE, they had required in the past that when you wanted to make a computer time proposal in the inside program, you would have to use 20% of this leadership class resources, as they are called, simultaneously. That means you would have to use 20% of 500,000 cores for your program. 100,000 cores, okay? That's what you should run on. So is there anyone who has done that here? Who believes you could run Ramses on 100,000 cores? Not officially. Yeah, that is, I think probably it will run, yes. And not efficiently, yeah, like my codes too. And that is really difficult. K-computer, you see 700,000 cores and so on. And there are two of them here are in Germany now, in Jülich. There's one in Italy, entry 9. There's one in China at 8. And this list changes every year. What is here on place 1 will now start sliding down rapidly. But it's quite impressive. Now, the other thing, look at the power consumption over here, last column. So this guy, this machine, this device takes 8.2 megawatts of power. And that is really a critical thing, because you can use these big supercomputers, for example, to do large calculations. I show you one example. The biggest particle number that I've been involved in, 300 billion. There are some now that have 5 or more than 500 billion. This is the Millennium XXL. This took only 3 million CPU hours, was executed on 12,300 cores, and then takes about 10 days to do. On the future Exaflop computers, that will be available in 2018. They have a 10 to the 18 flops are predicted, meaning floating point operations per second. So the current speed of the current machines in the top 500 was about, here you see the peak performance goes in the range of 20 petaflop already. 20 petaflop. So, but it's predicted that towards the end of the decade we will reach then 1,000 petaflop, an exaflop. Maybe. At least that's when you extrapolate the long-term trends. And doing the Millennium XXL on this machine, using that speed, would cut this 10 days into 15 minutes only. You could do a lot of those. But as I said, these petaflop computers take a power of say 6 megawatt. 6 megawatt. If you use the same technology to do a Exaflop computer, this is 1,000 times. So you then need gigawatts of power. And basically a power plant for it next to your computer. I don't think anyone will pay for this. So that means this is not going to happen. It's not going to happen. You see here a clear limitation of exponential growth, right? It's like this has to stop at some point, and we're right at this point. It has to stop. In the past, the power bill was growing exponentially. This has to stop. And this will be a huge change in this whole game, I think. That we have to reach the power envelope. So the predictions are that the maximum power envelope is maybe 20 to 40 megawatt that any government in the world is willing to pay for. So that is basically what this means. And so that's why also something like the green 500 list is now becoming the benchmark. So here the supercomputers are sorted by their energy efficiency. How many megaflops per watt do you get? Now, interestingly here, you see that these machines, I don't know, well, they all have, if you look at the top machines, the first 4 here, they have accelerator cards. So these are ordinary clusters here with Intel Xeons, but then they have Intel Xeon Phi accelerator cards. I get to this. They have here graphics card too, AMD's here in this case, and here Titan comes in at rank 3 with the NVIDIA accelerator cards, GPUs. Here at the Swiss Scientific Computing Center in Lugano, they also are accelerated with GPUs. And there you see basically that this GPU computing offers also the potential to get more floating point operations per watt, per energy spent. Of course, these are somewhat theoretical numbers. The problem is a bit that there are not many codes that can actually simultaneously exploit the power of the host system plus the GPU efficiently. These codes are an extremely rare species still. But at least theoretically, these are very efficient machines. And then there is a Blue Gene Q. This is also more general purpose, well, this is an interesting architecture too, which used to be blue genes. Without the accelerators, it would all be blue genes here. The blue genes are much more energy efficient than typical clusters. So I want to talk briefly now a bit about parallelization techniques. So when I was a graduate student, it was popular to build these type of clusters. Now, indeed, we had cellars where these things were plugged together. So universities, on cheap budget, you would. This was a time when it was realized that, whoops, the individual PCs, they had CPUs suddenly that were competitive in speed with the CPUs in ultra expensive supercomputers. So then people realized, oh, let us just plug in some Ethernet wiring here at the back end and put some off-the-shelf PCs from MediaMarkt or wherever into these racks. And this is called the Beowulf cluster, Beowulf-style cluster. And today, more or less, this has evolved into a commodity hardware. Now you have nice racks, professional racks, but basically they're wired together in the same way, in a way, and you use fancier networks also at the backplane. Beowulf cluster. And these are usually programmed with the MPI library. That means you have a distributed physical memory space. Each of the computers is really independently working. And just via the network connection, you start on it certain programs. And the MPI library is a technique where you start the same program on all computers with the startup mechanism. And then you need to explicitly program the data exchange and data communication between these machines. And all aspects of the parallel calculation you then have to design yourself in the MPI library. So, however, it's not the only possibility to program these things. There are also some higher level languages that allow different programming models. For example, the PGAS languages, parallel global address space languages, like Unified Parallel C or Co-array Fortran or Chapel. Just a quick question, who of you has heard of these languages? Oh, excellent. It's even worse than I thought, because it shows, so these are the favorite toys of the computer scientists, but the penetration into the scientific community is close to nil, right? Which probably shows that this doesn't really work very well in practice, despite all the advertisement they're doing. But maybe, these languages are also around for quite a while. They allow, basically, the idea of this is a much more convenient style of parallel programming, where some of the data movement you can have, for example, have a huge global array that's automatically stretched on the different compute nodes in these co-array Fortran and UPC language, for example. There are other languages that maybe have a bit more traction, especially because of Tom Quinn. So Charm++. This is an object-oriented parallel runtime that allows a certain style of parallel programming. And it's claimed that this is, if you decompose the individual pieces of your work in small enough parts, that this can be very efficient. And I think there will be application based in a new version of Gasoline or PKD graph is basically programmed in Charm++. Now, the other thing that is important besides MPI is that actually the individual computers are not anymore just a single processor. There are these days so-called SMP machines, symmetric multiprocessing machines. And this is this complex diagram here shows you the layout of a typical four CPU machine, where each of the CPUs is a quad-core processor. And this is how this looks. So actually, the processors here are these gray thingies here. This is the core 0, core 1, core 2, core 3. On the socket, the first socket here, which is the first CPU. This is a piece of the die, basically, has these 4 compute cores, which kind of run as independent processors. They have, each of them have a first level cache here. This is the very fast memory, which is crucial for high performance. Then a little bit, each one of them has a little bit bigger level 2 cache. Then there's a level 3 cache, which is shared among these 4 cores. And then there is a memory bank attached to this, in this case 32 gigabyte main memory. So this is the classical memory. And as you know, probably most of you, is that when the processor accesses main memory, the data is first copied in these caches. And especially in this fast cache, then if it's there, you can start to work on it really quickly. But this is a very small piece, very expensive piece of memory. And so this data that has not been used for some time will be evicted quickly. It might still be in level 2 cache and may still be in level 3 cache. And if a cache miss hit happens. So if the processor tries to access memory and a memory element is not in the level 1 cache, looks up the level 2 cache, then the level 3, and then it goes to main memory. But going to main memory means a long wait time, 50 cycles, 100 cycles, basically forever. You wait forever if you have to access main memory. And that's why you're not getting the raw compute speed, because most of the time you wait for main memory, basically, in poorly written code, for example, or not necessarily poorly written code, depends on application, sometimes unavoidable doing that. Anyhow, these 4 cores share their cache and they share access to this memory bank. And then you have another socket here and another socket here and another socket here. So in total, there are 16 physical cores in this machine. And on top of this, some of these cores, actually these days, they have something else. They support increasingly so-called hyperthreading or symmetric multithreading. This is something that the IBM chips support and the Intel chips also. Basically, the idea is there that because the cores wait so often for memory access, maybe you could, while they wait, let them do some work. But what type of work? Well, you have to give them another thread, basically another execution line in the code. Then they can, while they're waiting, the process can switch to this other thread, do something, and then the data is there, and they continue with the original thread. And this thread switching must be very fast. It can't be done in software at this level. And that's why some of these chips have so-called hardware threading, where you can overload the core. You run 2 or 4 threads on it, and these additional threads, they fill the gaps in the use of the execution resources. And you can compactify and you can max out the use of these resources. This sort of illustrates this diagram that these gray areas are execution resources that are not used on this superscalar processor and the multiprocessor. And then if you put multiple threads on it with this hardware threading, you then can use these gaps. And the Intel, they support, again, in their newest generation, two hardware threads, but IBM in the Blue Gene Q has this works actually a lot better. They support their 4 hardware threads on the Blue Gene Q, which is the current Blue Gene. And you actually really have to use them. You see a very substantial increase in speed if you can make use of these hardware threads. So there you basically can put on a single processor 64 threads. You overload every core 4 times. A complication, however, with these NUMA nodes is the following, that you can have 2 models for this. For example, you have 4 CPUs or 4 cores. They can share the memory. These NUMA nodes share the memory, but normally the access speed to this memory can vary. Here, these 4 cores have all the same speed to one memory bank, but the more common setup is something like this. You have, for example, 4 CPUs. Each of these CPUs has a memory bank attached to it. And that will mean that these 4 CPUs, they can read data that's in this memory with the normal speed. They can also read memory over here. But to do that, they have to go through some interface, which is, for example, the hypertransport in the AMD chips, go to this over this corner, first to this other process, then here, to fetch this data. That is slower. That's called the non-uniform memory access, NUMA. So you can write a code here where you're ignoring this, and all the memory is just one big linear address space. But then certain sections of this address space will be very much slower than others. And you better be aware of this. And actually, this is sort of called the NUMA awareness. You have certain memory affinity. Certain memory is present here, and this is normally assigned on a first touch basis. This is if you do a memory allocation on your code, you get memory in the memory bank you are on. Okay? So normally you don't care. You don't have to specifically think about this. You get the memory here if there's memory available. But what you then have to prevent is that this execution of your thread moves to another processor, because your memory will still be over here. And that is called thread pinning. You need to make sure that your execution thread does not move to another socket for maximum performance. Right, so MPI, the program model that we have here is that the program begins, and then we have different execution threads that are all communicating with each other, and until the program ends. So in MPI, data decomposition and all communication needs to be coded explicitly, as I said. This doing this well is unfortunately represents double here, a steep learning curve, right? So yeah, actually MPI program is no fun. So nobody does that voluntarily. And that's also why very few people actually end up doing it, right? Which also is a bit of a pity. But it's kind of like the assembly of programming in a way, right? You really have to deal with all of this moving of the data. It's not very pretty. On the other hand, it's well standardized and portable, so it's the one model of programming that has been really around for a long time now. It's very well established, and I think will stay around for a long time. So if you want to learn that, it's certainly a good investment. But the shared memory of the compute nodes that exists in these modern nodes allows also a more simplified parallel programming model, and that's called multithreading. I already mentioned, of course, all the time threads. What is a thread actually? You know that Unix processes are isolated from each other, right? So if you run a process on one machine and your friend or office colleague runs a program as well, you cannot interfere with his or her program normally, right? You cannot read his or her data. Of course, you can do something nasty, for example, still like using all the memory so that it stops, basically, some crash machine. But normally, you cannot interfere with this other processor. But a process can be split up into multiple execution paths. That's so-called; these are so-called threads, right? And that's really like that you just say, then these threads, they are just siblings of each other, and they are just different execution paths through the program flow. And all the data is shared between these different threads. And also the resources are shared, file handles and stuff like this, right? So this is possible, and they are then again shielded. So every process is basically can be a collection of threads. And these threads can be created by the programmer explicitly, through so-called Pthreads system calls, or via OpenMP. Just want to show you this here, how this would look like in Pthreads. Not sure whether you can read this, but here say some function, do stuff, and basically the work that's done is some loop here from 0 to 100, where we call some function, some expensive calculation 100 times. But then maybe I want to have is do this 200 times, and now I want to use 2 threads to speed this up by a factor of 2. And with Pthreads, the way to do this would be that you create a function here, call this evaluate, and this function now makes a loop from 100 to 200, where it calls this expensive calculation subroutine. Now with Pthreads, you would do it like this, that you would include the Pthread header library, the header, and then you would create a thread. That's done here with this function pthread create, and you basically pass it as argument the function that this thread, the subroutine that this thread should execute. And it will execute this, and once it's done, it dies. Okay, it's gone again. And that will mean that once you do it like this, if you run this program, then in fact, these 2 loops will be executed concurrently with 2 threads that are different. So if you have 2 cores, you will then see a speed up by a factor of 2. Okay, because you just now created multi-threaded code. Okay. Now this can be done also in OpenMP, but it can be done there more easily. OpenMP uses a so-called fork join programming model. You basically have your normal code. This is basically a master thread. This is our original processor. And then you can have parallel regions where this spreads or is subdivided in multiple execution threads where you do now work in parallel. And after this work is done, these threads vanish again and only your master thread survives. And after a while, you start the next parallel region. This is how OpenMP works. And the example that I just discussed in OpenMP would look like this. You have your function do stuff with the main loop, like it's from 0 to 200. That's really what you want to calculate. But now you say, I'm including the OpenMP header. And all you now need to do is to put a so-called directive, compiler directive, a pragma here, pragma OpenMP parallel 4. Now this tells the OpenMP compiler, this is a language extension basically, that the next loop after this pragma is supposed to be parallelized with threads. And the thread creation and the subdivision of which indices are mapped to which thread, etc., is done automatically by OpenMP for you. So that is really that simple. And compilers for this exist for C and C++ and Fortran. This really allows easy parallelization of existing code. Well, there are some subtleties here about locking and so on, which I don't have time to discuss. But in principle, it's relatively straightforward to do this. And thanks to the shared memory synchronization, data exchange, you can also hide workload imbalances here in parallel sections very easily. So this is a very good thing. And you can reduce with this compared to what you have in MPI, the overhead that we discussed for bookkeeping, for parallelization code, and so on, a lot, right? So that's quite nice. And for example, just to show you an example, if you have this situation that you want to parallelize something with MPI, for example, on a quad-core node, you have 4 cores here, and this is the amount of work you're doing. The wall clock time runs down here, and you see that this division of work didn't work very well. Maybe, for example, I didn't know in the beginning how long it would take to execute certain parts of a loop. So I subdivided somehow, but I don't quite know this, and here I was unlucky. This core 2 took a lot longer, and then you see that what counts in the end is when you're done with core 2, the others will wait. If you are doing this with OpenMP, you can then dynamically adjust to whatever each iteration, for example, how much time it takes here, and then you maybe have a priority queue or something where you hand out the work to these different threads. In anyhow, whatever you do, you can achieve it now here that they all have really perfect workload balancing, and they all finish then at the same time, and so you really see then a speed up by a factor of 4 in this case, and you can hide any, you can absorb any workload imbalance that you would have in an MPI code that way. So this is why this is quite interesting in principle. Of course, it only works at the level of a SMP box, right? So, and I get back to the implication of this later. But there is also a third level of parallelization, which is also important, which I should mention. This is namely that there are now so-called vector instructions on the modern processors. And they have recently become yet more powerful. So they existed originally, were introduced way back as for multimedia stuff, etc., to accelerate video calculations. But nowadays they are offering full-blown vector instructions for floating point arithmetic. And what this means is, for example, in the case of AVX, which is the newest generation of this, advanced vector instructions from Intel, they're also adopted by AMD now. There you have basically on the processor a large set of registers that are 256 bits wide. And these registers, they can do, with those you can do 4 double precision calculations in one instruction. That means in parallel. Or 8 single precision calculations, essentially at the same time as you can do an ordinary calculation. You can also do 4 square roots simultaneously, for example, right? Or 4 divisions. So that is meaning if you use those instructions efficiently, you can substantially speed up your code, right? Potentially with AVX, you can get factor 4 in raw performance for such floating point intensive calculations. So this is very interesting in principle. How can you use those instructions? Well, you can either use that the compiler will use them in an optimal way automatically. So you can switch on compiler flags that tell the compiler try to use AVX instructions. And then it will maybe use that, maybe not, you don't quite know. It's a bit wishful thinking to believe that they will make optimum use, at least at the moment. The compiler developers will certainly improve this. But if you think yourself a little bit ahead on how this can be done, you can actually get more out of it. You can also use so-called intrinsics to directly make use of those in your code. For example, you have a piece of C code here, do stuff. Okay, now I have here double vectors with 4 elements, A, B, and a result. And I would like, for example, I would like to multiply A times B vectorially, so element by element wise, and place it in result. And you could now write a little loop doing the multiplication. That would be the classic way, okay? You could also do it the harder way and put in AVX intrinsics, and that would look like this, that you include the header file for these intrinsics, and then you put an instruction, an explicit load instruction of this vector A into a register X, which is 256-bit, right? And you do this, such a load instruction in register Y. Then you multiply the stuff together in X, and then you store that X register again in the result. This is really assembler programming here, okay? Because the intrinsics that you basically, it looks like C code and looks like functions, but these are basically 4 assembler instructions here. This is much faster than your little loop over 4 elements. Okay, so if you really are fanatic about speeding up your code, then this is something you can try. And I should say the Intel Xeon Phi accelerator card. So this is basically the competition to the GPUs now from Intel, where you have a whole set of slow x86 cores, sort of reduced x86 cores. Those are slow, but they have, for example, they offer even 512-bit vector registers. So that means you can then do actually 8 or double precision or 16 single precision calculations in one instruction. That is almost like the streaming processes, of course, that are on a GPU. Coming to a GPU now, this is also very interesting. Those graphics cards were developed for the graphics. And here, turns out that as a side product, one was realized that actually they have become so incredibly powerful that it would be nice to use them also for ordinary calculations, not just for fancy game graphics. And the GPU has a different architecture than the GPU. It's not a general purpose machine. It has streaming processors, streaming data that are a little bit more stupid than the cores here. And much of the die area is used to create many more of these processors. So you have here intrinsically many more cores, if you wish. And these cores are quite fast, but they don't like to branch, for example. They won't like to, in groups of called warps, they want to do the same thing. So they are basically a little bit like these vector operations. They would like to do all the same thing and then stream through big piles of data and big calculations in an ideally relatively uniform form. So this is sort of threading on steroids, kind of, right? So you really have to, in this case, you have to employ 100,000 threads, for example, simultaneously, ideally, or tens of thousands. And in fact, in a grid, you can give every cell, you can make one thread, for example, on such machines. And here, the programming model is quite evolved, because what you have to do is so-called device computing. You have your host system, but then you have a computing device, and you need to communicate with it. In particular, you have to explicitly send data that you have in your host memory to the memory of the GPU. Then you launch a compute kernel there that does something with this data, does a bunch of calculations, delivers a result, and this result has maybe to be copied out again to the host memory. And if you can formulate your problem in a heavily parallel way, such that this streaming calculation can run efficiently, then this is a very attractive way to speed up some calculation and make it very efficient. Problem is that you normally have to make a lot of algorithmic changes to do this really well, right? And there are now actually compilers that offer automatic GPU parallelization and so on. And again, I think this is very limited in scope. To get a real maximum performance, you will have to do this by hand. So high performance computing, I think, offers in the next years really unprecedented opportunities for astrophysics. But the bad news is that this world of programming these machines is really a mess. You have now to do parallelization through MPI, OpenMP, GPUs, and SSE AVX vector instructions at the moment. And ideally, you need to combine all of this, really, right? Because the fastest supercomputers have these accelerator cards, and maybe you're only getting time on them if you are combining all of these things. Yes, and that's really hard, actually, because this has developed so rapidly that most of these codes don't really exist yet, but a few do. And those people who are first in the position to have that, they can, of course, make use of these computers, right? And I'm of the impression that many people just don't think hard enough about this, that if they don't tackle this challenge, then you're just left out of the game. That's the clear consequence. And this roadmap to Exascale is there are many of these roadmaps that you find on the internet, from the compute vendors, what you expect in 2018 in terms of computers. And here, this is a small script here, Exascale 2018, exaflop performance, system memory, 10 petabyte of RAM, node concurrency of order 1,000. That means 1,000 cores per node. So what you now run with your 1,000 MPI tasks is now one node. Okay, then you can go back to shared memory. That's the good news. 1,000 cores. But then the total concurrency is of the order of 1 billion. You have 1 billion threads in the whole system to keep busy in parallel. Right? Storage 300 petabyte, 20 megawatt power bill. And now the question is, of course, and I think this is just, I mean this quite seriously, do our problems, about all the ISM physics that Ralph and Nick discussed, for example, do we really have degrees of parallelism that can be expressed through 1 billion threads that run concurrently? I don't think so, to be honest. So, that will mean maybe it's not us that can use these machines. So that could be one of the consequences, but I think it's too early to give up hope. So, and now I'm actually at the end of my presentation, just on time. Are there questions? Yeah.
So do you think it's possible to build a compiler, for example, then try to automatically compile your code and run into the API GPU OpenMP system simultaneously? So you don't really need to do writing a special code for GPU, for example.
Yeah, I mean, this is what the compiler vendors definitely promise, right? I mean, you can go to the website, say whatever, of Portland Group or Intel, and you will see some flashy bullet points or automatic parallelization for GPUs and so on. And then you put up the cache and then go for it. I predict you will be disappointed by the results. So, I mean, there is just, I'm not sure whether it's possible or not. Yes, I mean, they will get better with time. It's a bit, I mean, this is really hard. I mean, it's the same, there is no compiler that can do a good job at automatically MPI enable a code or so, right? If you want to have automatic compiler-based parallelization, you need to go to PGAS languages. You know, you need to use UPC or CoArray Fortran. So this is part of the language standard, because then you express your code already in a way where the compiler can do something with it. You know, generic serial code will not. It's impossible basically to automatically parallelize on distributed memory. Yeah.
Is it possible that if you have a good load balancing routine and then you run on AMD, an AMD machine, you can actually experience that the Hyperthreading slows down your run?
Yeah. Yes, that's right. I mean, this is actually a common phenomenon. Let me maybe explain this a bit. In a diagram. This has to do with the cache coherence normally. For example, I mean, I showed this before, okay, and there are these caches, okay, and they, if you now have a program, for example, you run, it can happen even with just 4 threads here, but better if you have these 16 cores, and for example, you would want to run a serial code accelerated with OpenMP, and you let OpenMP use the whole machine, then you get 16 threads. And then you maybe have a calculation that does some of the threads, they do occasionally some write somewhere, and it's maybe even locked to void race conditions, so you're all fine. But then you discover if you put these threads, it's really awfully slow. You don't see the speed up. You wonder why this is. One of the common causes is that you have so-called cache coherence snoop traffic, basically, which in a way means, you know, if the process work fast if they can access their cache data here, but these NUMA architectures are cache coherent. That means you need to make sure that if another core writes at the memory location that you have in your cache, then your cache line is invalidated. Okay, and you need to refetch this from memory. And what then can happen, depending on your program, is that your threads constantly invalidate thread lines on other processors' caches, and that creates so-called cache coherent snoop traffic, and this can become very extreme, especially if you have like 16 threads that are run all for the same process, because then, you know, the cache coherence traffic also needs to grow across the crossbar switch to the other cores. For example, here, you know, you basically do something here. Maybe you make a write to main memory that can invalidate a cache line over there, and the processor will detect this, and it leads basically to an interruption of the process flow here until this is all fetched again from this memory and delivered over there. So basically these interferences in the cache access is usually the cause why these threads don't run with the full speed. And so you can sometimes see also decline in speed by putting more threads because of that.
Other question? Other questions? So if not, I think just before the break, and because Volker will leave very soon, I think just in 2 minutes, it's really the time to warmly thank him for this very, very interesting lecture. I'm sure you appreciate them. We learned a lot of things during this week, not only from you, but I think we learned very interesting thing from Nick. I don't know if Nick is here today. He teaches us how to create quiz, how to play with them. But I need some practice, so I created my own quiz, and it would be nice if you could answer to it. So I think you've convinced lots of people in this room that moving mesh methods are really the way to follow. So imagine that a student from a foreign institute, which is really interested in numerical techniques used in galaxy formation, come to your office and ask you for an advice for his PhD thesis. So what will be your answer? So you have 4 choices.
Okay.
So A is, well, try to do your best with the existing code based on SPH or AMR methods. B is, well, definitely you have to move to something new, write your own mesh code. C is, of course,
What's that?
just wait.
What was C again? I didn't get C. C. Huh? Okay. Yes. I think my honest answer is A. Yeah, just no. I think I didn't. Well, surely I was delivering my presentation such that the moving mesh technique was coming out as an attractive scheme, right? I mean, surely. I mean, I have worked on this, so I like it, but I don't think it is the only viable approach. It is, I think, a good approach, but not the only viable one. And I think, for the time being, just do your own thing, innovate, and just don't. Maybe sometimes you have to leave the ordinary path and come up with some new ideas. That is always refreshing. So I would recommend this. And of course, do interesting physics. I mean, this is it's still not about the code. Ultimately, you will see that, and I think this is also really comforting, that it's ultimately not it doesn't hinge on the code that you're using, whether your result is interesting normally or not. So the astrophysical result is sort of what should be at the center, and if you have an interesting insight there, probably you can have this insight with a crappy code too. Still, of course, for various reasons, it makes sense to have good codes. But I think that is really what you should focus on. And then the second advice would I give is, and the option B you gave is also, in principle, you should be dare to do things. I mean, if you don't like the tools that are out there, create one yourself.
Okay. Thank you very much. I think